All right, so hi everyone. This is my lab 3 for Physics 1 at Georgia Tech. And in this lab, we'll actually be finding the mass of a black hole when we're given the mass of a star orbiting the black hole, the position of the star each day for roughly a year, the mass of the star, and the position of the black hole during this time. So we know that the star in the situation goes around an elliptical orbit. So we know that the momentum of the object changes due to the fact that it's going to change direction as it goes around. So due to the momentum changing, we know that there's a force acting on it. And this force is the gravitational force. And since it's in space, we know nothing else is going to be acting on it, just because only gravity is going to be acting on it, at least as far as we know. Now, we can find the gravitational force using the formula for universal gravitation, which is force gravitation equals the universal gravitational constant, which is like 6.67 times e to the negative 11th, the mass of the star, the actual mass of the black hole itself, and then the radius squared, which is the distance between the black hole and the star. Now, if we solve for the mass of the hole, we get that the mass of the hole is equal to the radius squared times the force divided by the universal gravitational constant times the mass of the star. Now, the real question is, how are we going to find the force so that we can identify the mass of the hole? Because what we're given is the position of the black hole and the position of the star at any given point, which we can use to calculate r. The gravitational constant we can look up in any textbook or online. And we're given the mass of the star, but what we don't have is the force itself. So in order to calculate the force, well, we're going to have to find by using the momentum principle. So the momentum principle we normally see as the mass times the velocity over time, which seems pretty simple enough. But we can also see it as the change in momentum over the change in time, which is dp dt. Now, we can actually split this into a parallel force and a perpendicular force. The parallel force is going to lie tangent to the orbit and is going to basically determine how the star moves around. The perpendicular force is always going to be pointing at the black hole itself, which is mainly going to be the force of gravity in that situation. So if we look at the VPython code I made for this situation, or edited for this situation, we can see that, let's exit the calculation loop and go back up here. We use this to define the top part here to define the visualization, the graph setup. That's really simple. What we have here is the input of the mass of the star, the input of the original black hole position. Delta AT is going to be equal to a day because that's the time between our data points. Right here is where we have our star data put in. Down here is the important part where we calculate the velocity, because what we have is we have the x component of the velocity as it moves around, changing its x position, and the y position, which we're going to need to calculate the velocity for both of these. If we go down one more, here's the part where it gets tricky. So what we do is we split up the net force into two different parts. We have the dp/dt parallel, which is the parallel force, which is multiplied by p hat. Now p hat is actually the unit vector of the momentum. Since we want the parallel force moving in the same direction, we multiply it by p hat and we get the parallel force. And then we use the perpendicular force and rerun it, and we get this giant mess of, oh, look at all these forces changing at all this time. You can see the arrows moving, and the black hole is going to be about where my mouse is, and it's going to move for about a year, and it completes about a fourth of the orbit, about now, I think, maybe, yes. I think it's done. Okay, and we get that the final mass of the black hole was actually none of these. The final mass of the black hole is roughly 3.9803 times 10 to the 31st power, which is roughly 1 million times larger than our star. Now, if the mass of the black hole was changed, but the trajectory and everything was the same, we could actually use the code to evaluate the actual mass of the black hole again, because it just simply takes in the data for the position and calculates the force using the position and the mass of the star, and it should actually locate what it actually is.